like, no, I'm staying. So I was like, fine, I will go. And then he was like, no, I'm staying. And I was like, oh. If you want to use it.
Okay, so usual thing, guys. I realise there's not very many of us, and I'm going to assume that that's because of the linear algebra midterm later. But we do have quite a lot on this exercise sheet, so there's quite a lot of choice here for you to pick the most useful thing for you. Now, there is actually really a lot on this exercise sheet, so utilise the fact that you're allowed to vote more than once. What would you like to see at the beginning of the tutorial? So the options are, I've put question 1 and question 5 together. So let me just look at the full description. So I've put 1 and 5 together because they're both about calculating using the normal approximation for the binomial distribution. I put question 3 and 4 together because they're both about a sample of normal random variables. Question 6, which is a sample of Poisson random variables. 8 or 9, which is sort of moving into your next topic, which is about unbiased estimators. And question 10, which is about the properties of a proposed estimator. So give us some votes. Tell me where you're up to really with this material. But seeing as we're coming into midterms and it's a really, really long sheet, my guess would be we're focused on the beginning ones, but you need to give me feedback to let me know whether I'm right on that or not. Okay? So I'll just give you a couple of minutes to think about what you want to vote for, and then we'll go through something from the visualizer and have our tutorial in the format. Okay, so we've got just under half of you had a go so far, so let's have a look at where we're up to and see if anybody wants to change their mind about anything. So we've got quite a few people saying question 1 or question 5, about the binomial distribution and normal approximation, and quite a few people saying question 6 as well. So if you've not had a go or you want to change your mind, pile in and... Oh, okay, there we go. Right. All right, so that's definitely swung in favour of seeing question 6. Oh, and number 10 is coming from behind there. All right, so why don't we do... Ooh. Okay, why don't we do number 6, and then if you've not had time to do them in the free time for you to work, maybe try 8, 9 or 10 as appropriate for you, and we'll come back and we'll do one of those 3 at the end as well. Okay, it seems like while I've been explaining that we've swung towards 1 or 5 first, and then 8, 9, 10 at the end. Okay, so let's go with that instead. Okay, so of question 1 and question 5, I think I'll go for doing number 1. So what I've got is I want a random variable which tells me how many people are actually going to be showing up for this flight, and I'm going to denote it by y. And because there's only 2 options, they either come for their flight or they don't come for their flight, I can guess immediately that this is going to be binomially distributed. So that's great. Now, the parameter n in the binomial distribution is going to be the total number of people who've been given a ticket, so the absolute maximum number that could possibly turn up for this flight. So 267. And then the probability that they actually show up, so the probability of the positive outcome happening is going to be my parameter p. I'm going to put 0.94 in there because I was told there was a 4% chance that they didn't show up. Okay. So, what's the average number of people who turn up for this flight? I need to use the properties of the binomial distribution I know. So so the expected number of people who show up is the expectation of y. And from the properties of the binomial distribution, I know that this is n times p, the 2 parameters. This one's n, this one's p. So just over 250 people are expected to turn up. For the variance, I'm also going to use the properties of the binomial distribution that I know. So the variance of y from probability 1, I'm expecting this to be n times p times 1 minus p. And I can, maybe I should know these characteristics of certain key distributions, but I can also derive them using the methods in probability 1. And this. $15.058. Okay. So So the second part said, when can we use a normal approximation? And I really would like to use a normal approximation for this question, because I've got 267 as my value of n. So if I start calculating with the binomial distribution, I'm going to have 267 choose 1, 267 choose 2. I'm just going to have an absolute mess of a sum to try and calculate. So this is why I would like the normal approximation to hold. And the inequality that I've got that shows when the normal approximation is valid is the following one. So I've got to multiply by 9 the ratio p divided by 1 minus p, and 1 minus p divided by p. Take the maximum of these, and if it's less than the number of elements in my sample, then it's okay to use the normal distribution. So let's plug in the numbers that we've been given. So on the right hand side there, I'm going to have 141, because 9 times 0.94 divided by the 6% is going to give me 141, and that's definitely bigger than the other ratio. So 141. Now there was 267 people in my sample. So in our case, so we're allowed to use the approximation because 141 is less than 267. Okay. And then the third part, said, what's the probability that there's between 248 people on the flight and the flight's at capacity? Now I need to relate this to my random variable y, the probability that there's between 248 people and 255 people on the flight. And my first temptation might be to say, okay, y has to be between 248 and 255, and this is not the case. And the reason why this is not the case is that if more than 255 people show up, we've only got 255 seats, so the excess have to go on the next flight. So what this is actually saying about y is that y is bigger than 248. We don't need to worry about the top end because any more than 255 and we'll just chuck them on the next flight. Okay, so this is what I'm looking for. Okay, so the first thing I need to do in order to use the normal approximation is to do a continuity correction. So this probability is approximately equal to the probability. Now I need to go back 0.5 from 258 so that when I round my normal random variable, it's the minimum value is this to the nearest person. Okay, so this is my continuity correction. And here, x is a random variable which is distributed normally with parameters similar to y. So the mean of the random variable x is going to be the same as the mean of the random variable y. So this one has 200. So x has the same mean and variance as y, but it's normally distributed. And then now that I've got a normal random variable on the right-hand side here, I can standardize and use the table. So the first step is going to be to standardize so that I get a normal 0-1 distribution, and then I'm going to use the table. So to standardize, what am I going to need to do? I'm going to need to subtract off the mean off both sides and divide by the standard deviation. Now what's in the notation there for the normal distribution is the variance, so I'm going to need to take the square root. And then this manipulation manages to, I can replace the random variable x with one I'm going to call z, which is normally distributed with parameters 0 or 1. And this is something that I can look up in the normal distribution table or using R. So where am I going to be? This is going to be 1 minus the CDF of the normal distribution, evaluated at minus 0.897, and overall is going to give me 81%, approximately 81.51%. Okay. And for the fourth part, I was looking for something quite similar. I was looking for the probability that there's enough seats for everybody. And the tricky thing, or hopefully the tricky thing, is to translate this into something related to y. So translate from words into an equation about y, which I can then use exactly the same technique as I've done above on. So what is this going to mean about y? It's going to mean that the number of people who turn up y is less than the total number of seats on the plane. So y has to be less than 255. And then hopefully it's not a great leap to continue using exactly the same method as 3. And I'd like you to, I'll leave that bit for you to have a go at, and you can shout me if you've got a problem with translating the method over to that particular case. Finally, we were asked what's the probability that there's between 6 and 7% of passengers don't turn up. And I think there's more than one way of translating this back into something about y, but I I'll show you one of them, just one of them, and if you've used a different technique, feel free to ask me or Sarah Louise whether it's okay. Okay. So I'm going to say that this is equivalent to the probability that 93%, between 93% and 94% of the people with issued tickets to actually show up. And where's that come from? So if 7% of people don't show up, 93% of people do show up. The reason why that y is divided by 267 is because we're now looking at the proportion of people who show up, not the absolute value of people who show up. And very similarly for the 94% on the other side. And hopefully, you'd be able to replicate the technique in 3 and 4 in order to calculate this as well. Okay. So I hope that's enough of a hint to get you going on number 5, but maybe not the full solution, because I don't want to take up any more of your working time. So as previously mentioned, work on wherever you're up to. Sarah Louise and I will come around to answer any questions and help you with anything that you need. We'll probably come back maybe 45 minutes, just before 45 minutes pass, and we'll do one of the estimator questions as well, just to sort of kick you into gear with finding out whether estimators are unbiased and things like that as well. Okay, let's start. Yeah,
no
so,
accident.
yeah, so the idea is like try and think about it in terms of the one turn around check whether or not you can use your normal approximation.
Yeah.
Find the mean
65% support candidate A. It actually couldn't just okay. Now, I think this is a binomial. So basically you have 200 waters, right? And out of that, so looking at the water supports candidate A is 0.65.
sheet, so you know, if you give it to them, you're mainly revising for them, right? But you know, if you know up to like three, 4, 5, that's great. We're going to use the remote estimator to come out of our calculus, so that it would be more reduced for you. yeah, that's the value of the one. So you're going to need that one and the other way around as well. But that's, we're going in the right direction now.
Yes, so this is 0, right? And now when you do the variance, what do you want me to do? The variance is the variance is
What you can do is you can say what's inside the modulus is bigger than minus
variance is sine. Variance of x
it's bigger than minus 0. And then you have an equality like that, and then you come to try and find the probability that you might be able to
So what's inside the modulus?
Variance of y, x minus mg times 200 times 0.65 times 0.35
and then when I manipulate this,
divided by
I end up with the difference between
yeah,
this and this.
then plus
And manipulate this.
because you know it's really like variance of difference is just the sum of the variance.
Usually
I thought you did this one for the one.
less than 0.1.
So it's 200 times 0.65
But then we need to
times
limit it down.
0.35. So you simplify this, I don't have a calculator, do you have one? Can you simplify this first?
Okay.
Yeah, so
Wait, so how is Z distributed?
So
Probably this
Z
is
is
what-
going to be distributed one.
How do you?
And how do I decide on
you
that?
need to, because you're looking at the sample mean, right?
When I've got two
So you
random
need to
variables,
divide the variance by n, which is 25. So it's 122 divided by 25.
that they're both
Because
random, then the
remember,
combination is going to be
the variance of the sample mean,
if I've got any two random
the
variables,
variance divided by n, I think I should
add them
improve
up,
it
how do I
because
find the mean of the total?
If you've got any two.
Yeah.
there's no variance, it's just mu, mu is 112.
One,
Yeah,
how do I do it? The mean of x1 plus x2. Yeah, that's exactly right. So it's due to the linearity of expectation. The mean of the first one. So if I wanted to
then what you need to do is you need to,
x1 minus y1,
right now, so you need to
what would I do when I want to calculate the mean of
That's what I was thinking. Zero.
exactly what I'm saying, yeah.
So that's why you've got.
Yeah, yeah, that's why I've not done any increment. What happens to the variance of any two random
okay, now what you do is what you do is you need to standardize this. You know how to standardize. So you need to
I am asking how many.
zero.
You might remember from A level that you have the variance of one and then the variance of the other one, and you have that covariance.
Same thing here.
Yeah, briefly, I guess.
Yeah, just briefly. And then if they're independent, then you don't need to worry about the covariance at all. So you just sample and apply it, add up the variance. Now, variance doesn't quite behave in a linear way, because if you say had A times a random, like a constant times a random variable, then we take this squared as well. Right, so what we need to do with variances, then we need to add them up. So here I scaled by the constant to what the ratio is, but we should just, that's fine. So when you do x1 minus y1, you'd have normal when you go mean zero, then it's 2 times this, so minus 1.
2 times this.
Yeah,
Just
plus.
that.
Because I'm adding up.
Yeah. Okay.
Yeah. handle to actually get my numbers. You plug them into my normal table, jobs again.
Okay, yeah, that makes sense.
Is that good?
Yeah.
Okay, so just before we go, I just wanted to mention maybe one thing. Initially, I promised one of the later questions on this sheet, and I don't think many people are that far along, so maybe that's not the most useful thing to do. Instead, I just wanted to remind you of a couple of properties of random variables that are going to help you with questions 1 through 5 or 6 or so. So, quite a few places, including question 5, we were asked to find out whether like the difference between two random variables or the difference between two variances or something like that was within a certain range. So in question 5, for example, we wanted to find the probability that the number of people in sample 1 divided by 200, so the ratio of the number of people in sample 1 minus the ratio of the people in sample 2 was less than a certain value, so 0.1. And a lot of people ask me, so how do I know what the distribution of the left-hand side of this is? If I know what the distribution of x is and the distribution of y is, how do I know what the distribution of the left-hand side is? And I just wanted to add 3 things that will help you. So the first one is, if x and y are normally distributed, then a linear combination of them is also going to be normally distributed. So if x and y are normally distributed, x minus y, or x plus y, or x plus 3y, or whatever, all of them are going to be normally distributed. The second one is for any pair of random variables x and y, they don't have to be normally distributed or anything like that. How do we find the expectation of a combination? So how do I find the mean of some kind of combination? And in this question, I'm going to want to take a is equal to 1, b is equal to minus 1, but this is going to hold for any constants a and b. So the expectation behaves linearly. So I can take the expectation of the first term and add it to the expectation of the second term. That's fine. It's also the fact that I can take out the constants as well. So it's independent of the constant a and b. So I can take the expectation of x and multiply it by the constant a. So it's what's called a linear operator because it's got this property. And that's very, very handy with finding the distribution of the left-hand side there. Because if x and y have the same mean, then when I take the difference, it's always going to be a mean zero random variable. And the final thing that's going to be helpful is if x and y are independent, how do I calculate the variance of a combination? Well, again, I've got linearity of variance, but the constants are going to behave in a different way. And you can see this by writing out the full definition of what the variance is for a particular random variable. And so the A's are going to come outside, the A can come outside the variance, but it's going to be squared. The B can come outside the variance, but it's going to be squared. And again, I've got the linearity there as well. Okay, so what's going to be the distribution of x divided by 200 minus y divided by 200? I'm going to have to combine the distributions of x and y using these rules, and I'm going to get a normal distribution which I can then standardise and crack the handle and do my standard method with. So that's handy for all of these questions where you're asked, are the means of two samples quite close together or quite far away from each other or whatever else like that. And I hope that's kind of shed some light on why the calculations are the way that they are. Okay, so thanks for coming along. Best of luck with linear algebra later on, and I'll see you all next week for our final lab.
Thank you.